So far that was not that bad, was it? Just maybe we went a little bit faster with the last part, the use of the connected components and the different functions all at the same time. But I hope that you got the gist of it, and most importantly that you understood that you already know all the functions that are going into that code. And now it's your job to just get used to them and looking at the code and understanding exactly what it is doing. As a result, we got many patches of different bushes. But what we did not get is the information of what species each bush belongs to. Okay, and this is going to be extremely important, because in order to train any deep learning network, we have to provide this network with the image information, but also with the correct answer to the problem that we want to solve. Deep learning networks do not invent anything new. They just learn, they just fine-tune, they are just fine-tuned to reproduce some information that we already give them. So here we have the data, but we don't have the information that shows the problem that we want to solve, that expresses the solution to this problem. In particular, here we would have to associate, we would want to associate to each type of patch a label saying this is, I don't know, Kiaraboku or Sakura or any of the 6 possible types of subalpine patches that happen in this side of Zhao Mountain. So because we don't know what each species every patch belongs to, we are going to rely once more on the opinion of the forestry people, and we are going to have the different files for the different species: Kiaraboku, Nanakamado, Inutsuge, Matsu, Sakura, and Kaede, which are all species of subalpine bushes. Some are evergreen, some are deciduous. That's all going to be part of further research, and you will be seeing some of these in future sessions. But for now, and going back to GIMP, we have the mosaic that we used to have and the treetops that we already saw. Okay, they are here, but let's not look at them at this moment. At this moment, what we have is, for each species, a binary mask that shows what is the position of the different patches of that species. This is the one for Nanakamado, for example. I think Kiaraboku is a very frequent one. Yes, Kiaraboku. Okay, and we can also do the opacity trick again and go a little bit deeper inside of this to see examples of, for example, Kiaraboku patches. Kiaraboku bushes. Okay, so these guys are Kiaraboku bushes, and I could even go as far as show some treetops here, showing me that there are several bushes in this area, showing me Kiaraboku. Okay, so I can see how the information is organized now, but I want Python to have this information in a way that it can process too. So first of all, we plot the different masks. Okay, you have seen them a little bit in GIMP, and you can see them in some more detail here. Be sure to do that. But now what we want to do is transform, first of all, this number of different files into one single label image. A label image would have the same size as the mosaic and as the different layer binary images. It will have the same size, but instead of having either the RGB information that the mosaic has or the binary information that the layers have, it would have a code that would indicate for every pixel what possible class it belongs to. Okay, and to do that, we define this build level image function. It's a very interesting function that uses some of the things that we have already seen. Okay, first of all, I'm going to receive something called a ground truth list, and going to call it with something called GT. What was that? Oh, here it is. GT was built using, again, a list comprehension and calling read binary mask over all of the files in the site5 folder that had names in this list for name in GT names. Okay, so I have gone to my folder and looked for something called Kieraboku site5 Kieraboku mask.png and write it with as a binary mask and add it to a list. And then the same for Nakamado, Inotsuge, Matsu, Sakura, and Kaede. So I have a list of images. I'm now giving this list of images to my build level image, and what I'm doing there is basically using a code. So the first label that I rate is going to, the first push class that I rate is going to have the code 1, and the second is going to have the code 2, so that will likely be, that Kieraboku will be code 1 and Nakamado will be code 2, and so on and so forth. And I'm going to be, I'm going up and down. I'm going to be just reading each of the binary masks in the GT list, okay? Taking it, and then I'm going to modify my output, saying that for all the pixels that are 0 in my mask, so all the pixels that are black in my mask, so all the pixels that show where, in this case, Sakura is or Nakamado is, okay? For all of these pixels that interest me, I'm going to give them a code in the image, and I'm going to modify label image for all of these pixels and give them for Kieraboku code 1, for Nakamado code 2, and so on and so forth. And when I do that, I'm going to end up with a kind of image like the one that I'm superimposing to the mosaic here. Okay, I'm going to have all the different regions, all with different colors, all with different values. And this is what we call a semantic segmentation, or a label image in this case. An image that contains at each pixel the class that that specific pixel belongs to among all my, in this case, bush species classes. Okay, so once I have this, then it's pretty easy to connect the two things, the patches without a type and the types of each pixel. So, because I have a list of patches, it was called romantically patches, and the list of their centroids, their coordinates in CS, I'm going to define a function called patches by type that uses also the ground truth names, because I don't want to store simple codes. I will use a dictionary to store names and have a look at this, but it's not the most central thing here. And I'm going to take the list of centers and the patches and the label image, and what I'm going to do at each point is just take the label image called here labels and look at it, look at the pixel in each center, and you will notice that I have had to invert the coordinates, because the coordinates in OpenCV go yx and not xy. That's why here we have a 1 and here we have a 0. Okay, and I'm going to read the code that I can find in that centroid. So I'm going to consider all the points that I had here. For each of them, I already cut a patch, so I'm considering this patch along with the list of coordinates that I computed before. So for each patch, I'm considering its coordinates, the image of the patch, and now I am going to the label image that we have made and look at what class it belongs to with this code. Okay, I'm looking up the code in the labels image, and then I'm returning, I'm assigning that to a dictionary that will contain a list for all the patches of that type for each of the codes. So I will create a dictionary that will contain not a dictionary, a list that will contain in each position a tuple with the name of the code and then a list of the patches that belong to it. Okay. And then I'm just going to traverse that and name every patch with an identifier, a number that will grow, and the name of the class that it contains. So for all Kiraboku patches, I'm going to call them Kiraboku patch, and then the number will change. And I will end up with a folder called patches if you don't touch anything in the notebook, and you can also change it if that's convenient for you, that will contain all of these small images that contain all the different patches and that have names that contain the name of the class that they are imaging. In future sessions, we will start with this folder that already contains all of the information in a very well processed way that now I can feed to deep learning networks, and we will do just that. We will need first to think about how deep learning networks in PyTorch read data, to understand how that works, and to code a class that will do the translation from this folder of images to something that PyTorch can execute and can run through deep learning networks. And then we will have to define the deep learning networks, train them, run them, all that good stuff. But for now, we are finished. We have achieved our goal in the form of this long list of patches that show me all of these images that we have stored. So we have used very basic OpenCV methods to read images, find the centers of points with the connected components one, see what is in an image, to check the code from the label image. We have used them sometimes as NumPy vectors when we wanted to add them or to change them all the pixels at the same time in a convenient and fast way in the function where we built that label image. And we have done all of that using real data and real annotations from experts. I hope that you will get a feeling that this is all a little bit complex in the sense that it has many pieces, but that each of those pieces is pretty simple and that you already know how to use them. So have a look, try to reproduce what we have been doing yourself, and hopefully you will get convinced that you can do that for your own research. In following sessions, we will keep using this data for, let's say, loftier purposes, and we will finally reach the deep learning part of the course that was what motivated most people from the start. Until then, see you in the next session.